All right, this is Bob back again for part 3 of the 4-part series. And this is part 2, quantifying environmental releases using a watershed approach, and specifically is using a back-of-the-envelope calculation. This whole idea that we need to have ecological indicators to tell us how much water we need, or that we need a complex model. Let's just start with a simple back-of-the-envelope approach, because with that we don't need either of those two, and we can move forward. So here's our back of the envelope that we're drawing on. And if we take that Cypress dome out and lift it up here, you can see with the Cypress dome, we'd expect to have a certain depth of water over a seasonal duration, ideally in an undisturbed watershed. So the depth in feet and duration in months of water in the center of that dome is directly proportional to direct rainfall on the upstream parcel of land over top of it, and overland flow, plus overland flow. Now, if we block that overland flow and divert it down a canal, then our depth and duration of water in the Cypress dome is going to diminish. And that's the case we're confronted with in the West Feeder. So what do we know? We know our clouds, right? Here come the clouds, and we know that they, over the long term, produce 53 inches of rain per year over an 81 square mile area. How do we figure out 81 square miles? Well, again, back of the envelope calculation, this little red box is 9 square miles, and we have about 9 of them. 9 times 9 equals 81 square miles, times 640 acres per square mile equals about 52,000 acres. So that's our watershed area we're looking at. So here come the clouds again. They rain at about 4.42 feet of rain per year. Remember, that's the 53 inches over a 52,000 acre area. So our total volume of water is about 229,000 acre feet of water per year produced by the rain in that area. So we go back to our back of the envelope. The dome is the depth in feet and duration in months, and the dome is directly proportional to just direct rainfall now. We don't have that overland flow, but and that rainfall is 229,000 acre feet per year. Now, if we brought back that overland flow by putting breaks in the canal and releasing water south, then all of a sudden we can increase the depth and duration of water in our Cypress dome, right? So the question is, what is the proportion of that overland flow? Well, for argument's sake, I looked at the upstream watershed north of the West Feeder, and it's not as big as we see in the main flowway of the Everglades. For example, in Everglades National Park, the rule of thumb is 80% direct rainfall, 20% overland flow. In the water conservation areas, the rule is 70% direct rainfall, 30% overland flow. So in this case, let's just go with 5 or 10%. If we say that overland flow is equal to 5% of the annual rainfall, we're talking about 11,000 acre feet per year. If we're saying that overland flow is equal to 10% of the annual rainfall, it's about 23,000 acre feet per year. So for how long does that overland flow seasonally persist across the landscape? Well, again, we're looking at the sheet flow season as being this late summer, early fall period. And if we look at the historic data set for Big Cypress National Preserve, this is a surface water flooding history for Big Cypress National Preserve. The cooler, and it runs from 1990 to 2015, and then across from January to December. It reads like the pages on a book, and we are right here, right now. Anywhere you see the cool colors is where water levels are at its highest, and that persists, that sheet flow condition, on average for around 4 months per year. So what is the flow rate that we're looking at? We know the volume. At 5%, it's 11,000 acre feet per year, and we know the duration, months. So we just spread that release volume over a 4-month sheet flow season, and we get, at overland flow at the 5% value, equals 47.5 cubic feet per second. And if we do it for 10%, it's 96 cubic feet per second. Pretty easy calculation. So let's do a quick comparative glance. Is that 96 cubic feet per second, is that a can of Coke or is it a 5-gallon water jug? Where does it rank relative to flows in South Florida? Well, here's where the 10%, 96 cubic feet per second, ranks relative to some of the other major water control structures in South Florida, computed as an average annual discharge from 1998 to 2012. So if we look at the big flow maker in town, it's the S79 at the tailwater of downstream end of the Caloosahatchee River. That on average is discharging over 1.25 million acre feet per year. Whereas if we look at the S12A, we're talking more in the neighborhood of what? Between 50 and 150, around between 50 and 70 thousand acre feet per year. So we're on a smaller order of magnitude with what we're suggesting would be a reasonable amount to send south of the West Feeder. And here's the S12A. It's really one of the smaller major flow structures in South Florida, and what we're proposing would be smaller than that. What our 10% is more comparable to, that 96 cubic feet per second, is one of the individual bridges on the Tamiami Trail within Big Cypress National Preserve. And in particular, as a comparison piece, I wanted to look at the bridge at Clyde Butcher's Gallery. That's very similar. We're looking at, again, that Clyde Butcher's Bridge flows at just under 20,000 acre feet per year, as measured from 1998 to 2012 as an average. And here's a picture of Clyde Butcher's Gallery from the air. And here's a look at a nearby bridge, just a couple bridges down, Bridge 105, from the ground. So this isn't a huge structure that we would associate it with what you see in the Everglades, possibly because this is more a Big Cypress example. And again, we're talking the upstream watershed north of the West Feeder is not as big. So that's the back of the envelope calculation. I think absent without having to go in and figure out the exact ecological indicators and targets, and without having to assemble a complex model, we've started a dialogue on what's a good starting point for thinking about an environmental release to the south, and helps us answer these additional questions, because lots of questions still persist. Is how much water can be diverted from the West Feeder? That's our next question. How much new water, if needed, could be brought in? That's another question. How much water could be spared could the Seminole tribe spare from their developmental uses of the water to send it south to the natural areas? And what re-engineering would have to be done, including thinking about where those release points would be. So this leads us to the fourth installment of our four-part presentation here, which will be covered in the next presentation. Thank you for your time.